Welcome everyone to the 7th online seminar of the ISSI-BJ On Things to Come seminar series. You can see in the webcam Professor Tomohiro Usui of the Japan Aerospace Exploration Agency. Who will talk today about the MMX mission. You can see in the webcam also the Executive Director of ISSI-BJ, Professor Wing-Wen Ip. And I am Laura, I'm the PR and Editorial Manager of ISSI-BJ, and thank you once again for being here. Before I give the floor to Professor Ip and to Professor Usui, I would like to say a couple of words about ISSI-BJ for those who are not familiar with our institute. ISSI-BJ, the International Space Science Institute Beijing, was established in 2013 thanks to the cooperation between the International Space Science Institute in Bern, Switzerland, and the National Space Science Center of the Chinese Academy of Sciences. We organize a wide array of events, all aiming at the advancement of space science studies. So we cover a wide range of disciplines, all in space science, and we organize workshops, forums, international teams, working groups, and so on. So we always welcome actually proposals, the submission of proposals for scientific cooperation and research. As I mentioned, this is the 7th seminar of the On Things to Come webinar series, and this series focuses on ongoing and future space missions. We have the upcoming one in January, and again today the seminar will be on the Martian Moons exploration mission of JAXA. So with further ado, I would like to give the floor to Professor Ip. Thank you once again for being here.
Yeah, thank you very much, Lola. So, I mean, all of us heard of this very successful sample return mission from Hayabusa 2 of JAXA, and just recently the sample return of the lunar samples from the moon of Channel 5. So it's really nice to have today, to hear the talk, to chance to listen to the talk by Professor Tomohiro Usui on the Phobos mission, because this will be the next sample return mission. We are full of expectation. First time, have some sample from the Martian moon. Later on, he will tell us about why it's so interesting. But first, let me say a few words about Professor Tomohiro Usui. He got his bachelor degree from Tokyo Tech, and then his PhD from Okayama University in 2004, I think. And then he have spent his postdoc year in Tennessee, University of Tennessee. Yep. And sometime in NASA Johnson Space Center, I think. And then since 2018, he's now a researcher at ISSI-BJ. In fact, he's a professor there, full professor. And if you look at his website, he has a large team, of young scientists working with him. Himself is very young, and he now spent a lot of time working on the Phobos mission. I just checked that recently he has a paper called is here. He called the importance of the Phobos sample return for understanding the Mars Moon system, and I'm sure he's going to give a summary of that paper. But let's first welcome Professor Usui. Please, Professor Usui. Thank you.
Well, thank you very much for the introduction. Yes, I'm Tomo Usui from JAXA, Planetary Science Department at ISSI. First of all, thank you very much for inviting me to ISSI-BJ seminar. So I'm delighted to present the 3rd Japanese sample return missions following the Hayabusa and an ongoing Hayabusa 2. These are the asteroid sample return missions. So next to these asteroid sample return missions, JAXA plans Phobos sample return, Martian Moon sample return, called Martian Moon Exploration, MMX. Today I'm giving a talk about the quick overview of MMX, including the mission profile, instrumentation, and science goal. I think you can hear me well, right?
I think the problem is solved. I haven't received any other request issue. Please let us know in the chat.
I can see the chat.
Yeah.
Can I continue?
I think so. No one is writing, so I think it should be okay.
All right. So you can see the next page, like mission. Right. So
yes.
Right. Thanks. Here's a timeline of the brief timeline of MMX. JAXA officially approved the MMX in February 2020, 10 months ago, now in phase B. So we are going to launch the spacecraft in 2024, and it goes to Phobos and Deimos, do remote sensing observations and in situ observation on Phobos, and then retrieve the samples greater than 10 gram from Phobos and return to the Earth in 2029. It's about the 5 years mission, 2024 to 2029. And if it is make it, and MMX will be the first sample return mission from the Martian satellite, of course. So why Phobos? Why we will explore the Martian satellite? First, I believe it is because the Martian moon system is likely to preserve the original information about the planetary embryo that are created very early in the solar system. So Mars is located at the outermost edge of the inner rocky planet region and has a mass about 1/10 of that of the Earth. This figure on the left shows an accretion time. On the right shows the accretion time scale inferred from the hafnium tungsten isotopic radiogenic decay system. The model, the figure on the right, indicates that the Mars accreted very rapidly and reached the present size within 10 million years after the birth of the solar system. So such a short time scale is consistent with the standard planetary embryo origin. Information about planetary embryo is recorded by samples from Mars and its satellites. A variety of radiogenic isotopic decay systems tell us the timing of Mars differentiation processes like magma oceans and crust mantle recycling. And all of these processes occurred within the first, look at the figure on the left. So all these processes like magma ocean, the crust formation, then the accretion of core formation, all of them occurred within the first 50 million years. One example is that the coupled neodymium tungsten isotopic systematics of the Martian meteorites shown on the right on the figure, that indicates the timing of silicate differentiation occurred mostly less than the 30 million. So the point is that I think is these Martian meteorites preserve the source heterogeneity formed in the early magma ocean stage. These isotopic systems suggest that Martian mantle differentiated very early and did not experience the later global mixing. So this is not the case for the Earth. As you know, we have a moon forming giant impact on the Earth, and we have a plate tectonics, and also which these late forming events almost completely erased the primitive information. So this is the one of the example. How what is the building blocks of the Martian moons, Phobos and Deimos. This figure shows the result of the high spatial resolution SP8 simulations done by my colleagues, the Hyodo and the Genda et al. And the figure on the left shows mass fraction versus the kind of an impact angle. This is the model simulation of the impact model, and an impact angle versus the mass fraction. And blue and red lines indicates the mass of the impactor and the Martian materials that would constitute the Phobos building blocks. And you can see that if the Martian moon formed by a giant impact like Earth's moon, at least 35% of the Martian materials could constitute the Phobos the building blocks. So mostly Martian. Figure on the right shows cumulative fraction of disk particles and their original depth from the surface of Mars. So this original cumulative fraction data simulation suggests that the most of the mass comes from the deeper than the 60 or 70 kilometers. So compared to the typical crust thickness of Martian crust, which is like 30 to 6 kilometers, that would tell us that some materials comes from the Martian mantle. So if you go to the Martian moons, you have information about the Martian mantle as well. Let me talk a little bit about the geology of Mars. So the Mars surface is currently arid and super oxidized, but it used to have an Earth-like water cycle, resulting in the formation of a variety of aqueous alteration. Here's an illustration: aqueous alteration materials, minerals on the surface. Okay, this map shows distribution of aqueous minerals such as the phyllosilicate, which is clay, chlorite, and carbonates and sulfates. Each of these aqueous minerals formed under different surface environment at different age, as shown in this schematic illustration. Age as a function of age versus the distribution of alteration minerals. For example, in ancient water-rich conditions, like here, I'll show in the schematic diagram, ancient water-rich condition for clay minerals, followed by a relatively water-poor condition in the recent past, from left to right. So the point is that the Martian surface record historic evolution of environment. So go back to the Phobos sample return mission. Why we go to Phobos and Deimos? The point is that the regoliths of Phobos and Deimos contain the Martian building blocks, as I said, impactors, late accretive volatiles, and ancient Martian surface components. So therefore, the Phobos sample return mission is expected to constrain the initial condition of the Martian moon system and gain vital insight and information on the sources and delivery process of water and hopefully organics into the Mars and inner rocky planets. So a bit of talk about the MMX. MMX has two major science goals. One is to reveal the origin of the Martian moons, to make a progress in our understanding of planetary system formation and the primordial material transport. The goal number two is to observe processes that have impact on the evolution of the Mars system. That would give us a new vantage point and to advance our understanding of Mars surface environment transition. Going to the system engineering topic apart from the science. As I said, MMX mission is a 5-year trip from the 2024, launch in 2024 to and then back to the Earth in 2029-ish. 5 years trip. We're gonna use the chemical propulsion system. So it will take an interplanetary flight, 1-year flight from 2024 to the summer of 2025 for the onward travel and the state circum Mars orbit in 3 years from 2025 to 2028.
Professor Usui? Hello?
Hello.
Yes, you're back. I think your connection was maybe down for a couple of seconds.
Okay, back to this slide, and then so I have back to the circum Mars orbit, like 3 years from 2025 to 2028-ish. During the 3 years circum Mars orbit, we gonna do at least one landing operation onto Phobos, or hopefully two, but at least one, and to get the 10 grams from Phobos. This is not just a touch and go stuff, but landing. So here's the spacecraft configurations of this preliminary design. We have 4,000 kilograms, 4 tons for the launch mass, including the chemical propulsion, like 1.9 kilogram. And also the spacecraft consists of the 3 modules you can see on the right. From the top, you see the exploration modules. Most of the remote sensing instruments are equipped with this exploration module and with legs. And in the middle, you see the return modules, and also you can see the sample return capsule also be with the exploration modules. And on the right, on the bottom, you see propulsion modules, and most of them chemical propulsions are in. We're gonna throw it away when we reach the Mars orbit insertions. Okay, science instruments. We have 7 or 8 science instruments as you count. And the point is that the MMX is a JAXA's mission, but it's also the very international, international-wide mission supported by NASA, CNES in France, and DRL, Germany, and also ESA as well. So we have 2 cameras, visible light cameras, wide-angle multi-band cameras, and also the telescopic cameras. And also we have the gamma-ray neutron spectrometer, which is provided by NASA. Actually, APL, Johns Hopkins University, will make this instrument. We're gonna have near-infrared spectrometer provided by the France group, and also we have a LiDAR, dust monitor, and then mass spectrometers. And also we have a very small, that kind of size of the more bigger than that, rovers that would give us by a cooperation with the CNES and DRL. And this rover has a main 3 instrument, a Raman mass spectrometer, radiometers, and cameras. So back to the science again. We have two competing hypotheses proposed that were proposed for their origins. One is capture of asteroid, which is consistent with asteroidal surface spectral type. They are actually a D or T type we call infrared spectra. On the other hand, in situ formation by an impact, like a giant impact hypothesis that we have for the Earth's moon, this model, this hypothesis is consistent with the dynamical properties such as low eccentricity and an inclination. So origin, you can see on the left, this figure shows the near-infrared spectrometer, near-infrared spectra of Phobos surface in blue, and compared with those of the carbonaceous chondrite like Tagish Lake, Miguel, and Martian. You can see on the green, red, and gray. And such a D or T type spectra
Professor Usui?
Professor Usui, can you hear us?
Yeah, I think his connection dropped. Let's see if he can come back.
He said he's back.
No, it was a while ago. We tested the platform with him. The connection was okay, but yeah, Professor Ron, yes. Let's wait a second. Okay, but we cannot hear you, Professor Usui. Moment of patience. Maybe you can try without the camera, your webcam, just by sharing your screen. We still cannot hear you. Apologies, everyone, for the interruption. It's the first time. And maybe the connection is not... Professor Usui, we still cannot hear you. Still in blackout, yes, unfortunately. I see he's left the room. Maybe he's coming back after refreshing the page. Yeah, he's back. Let's see. Yeah, the screen is black at the moment because no one is sharing the presentation. But yeah, I think it's his connection problem, but hopefully it's fixed. Professor Usui? Yeah, maybe you can turn off your camera, your webcam.
How was it?
Yeah, let's hope that the situation is more stable.
Sorry for that.
Problem can happen.
Yeah, All right. I don't think JAXA's network is so weak, but it's the yep. Hold on. We're gonna start. Yep. Thanks. Right. Should I start again?
Yes, I think now it's back.
All right. So the figure on the left, as I said, shows the near-infrared spectra of Phobos and compared with the those of the carbonaceous chondrites. And then this figure shows that such a D or T-type spectra is consistent with a captured origin. So if the Phobos and Deimos are giant impact origin, instead, these spectra reflect either impact-related dark glassy debris or thin surface veneer or regolith, or just a result of the space weathering. So, but the MMX will test this hypothesis because we have a gamma ray and neutron spectrometer that would give us an elemental compositions, and also that we have a sample analysis. On the contrary to the spectral features, the dynamical properties are consistent with the impact origin. For example, the Phobos and Deimos have a very low eccentricity, like 0.0015, something like that, as well as very low inclinations, like 1.0 or 1.1 degrees. Such a low eccentricity and inclination clearly suggests the impact origin. But if the Phobos and Deimos are captured origin instead, it should be, I think, the gold mine for astrophysicists, because we need a new dynamical model to reconcile the dynamical properties and the hypothesis. Okay, so this slide shows the one of the examples of the MMX science payload. One is the visible and near infrared spectrometer. We call the Martian Moons from Lesia, France. Spectral range covers the range from the 0.9 to 3.6 micrometer. That would covers the absorption feature of organics and water ice as well, with the spectral resolution of about less than 10 meter per pixel from the altitude about 20 kilometers. So we can see, I think, hopefully distribution of the blue and red unit of Phobos and Deimos could be reviewed by the Mills instruments. On the other hand, we have gamma ray and neutron spectrometer. We're gonna call it the Migane. That was built by the APL Johns Hopkins University in the US. The great advantage of this instrument is that this instrument can directly determine yield, elemental abundances of magnesium, iron, oxygen, silicon, and hopefully other minor elements like sodium, calcium, thorium, uranium, and probably for sure the hydrogen in it and the carbon and chlorine. And another point is that the penetration depths of the gamma rays down to like 1 meters, that would give us average composition of the Phobos' crust, and also the iron, silicon, oxygen combination of these elements could differentiate a chondritic and the chondritic compositions. And also the MMX is the sample return mission. This is a paper by myself and Impress, but it's published a few months ago in a Space Science Review, and thanks to ISSI, because this paper was originally my presentation at the ISSI-BJ workshop, and that is a so great moment for me to present, and also to hear the other sample return missions. And now we're gonna publish the paper about the expected characteristics of Phobos and Deimos as a kind of function of the captured asteroid on the left and an in situ formation of the right. This is too much detail, so if you are interested in the expected characteristics of the Phobos samples, please just Google, goes to my papers, just Google like Usui Phobos sample return, and you will see my paper. Just wanna give you a highlight of this. Isotope is the most promising fingerprint for us to get to reveal the origin of Phobos and Deimos. You can see that this figure shows the relationship between the oxygen isotope. This is we call the capital delta 17O. That is the deviation from the terrestrial values. The 0 is the Earth's values, and also that you could see a fractionation of the 16O, 17O, and 80O. We're gonna consider that, and there is a kind of a difference from the terrestrial fractionation line, 0 to the -3, 4, 5, 6. This is a kind of a deviation, a Palmilage deviation from the terrestrial values for oxygen isotope. The x-axis is the mu, we call the mu50 for chromium. This is also non-radiogenic, stable isotopic of the 50 for chromium. As here's a palmilage on the oxygen. This is the palmirium difference. So the 0 is the terrestrial values, and also the 50, 100 parts per million difference from the Earth's values. Now we have very nice mass spectrometer that would give us such a short difference between the parent body like Mars, Earth, and the carbonaceous chondrite parent body, and then the ordinary chondrite parent body, and the achondrite parent bodies. So once we get the sample back to the Earth from Phobos, and then plot the Phobos regolith, Phobos oxygen and chromium isotopic composition onto this diagram, you'll see that this could be the captured asteroid similar to the chondrite, carbonaceous chondrite parent body, or ordinary bearing carbonaceous ordinary chondrite parent body. Or if you plot the Phobos in between Earth and a carbonaceous chondrite, something around here, that would give us a hint or evidence to support the giant impact hypothesis that would impact her as a carbonaceous chondrite and a Mars as a main body. Another interesting story for MMX is that Mars ejector could also exist in, sorry, in the regolith of Phobos. Give me a minute. All right. Figure on the left shows the numerical results of the numerical simulations showing the spray of impact ejector on the Phobos orbit. This black line indicates the Phobos orbit orbiting close to Mars, and these are the Mars impact ejector comes out from the Martian surface and is sprayed on the orbit. Because the Martian moons, Phobos orbit around very close to Mars, and then like more than 4 billion years, the Phobos have swept these particles in the billions of billions. So that as a result, some of the Mars ejector should have existed on the regolith of Phobos. So the point is that Mars ejector on Phobos is experienced to much lower launch velocity compared to the Martian meteorite. That would give us probably preserve the more original information about that. Here is another simulation done by my colleagues, Ryuki Hyodo, about the peak pressure versus the ejection velocities. And most of the Phobos samples experienced much lower launching velocities. And then I guess that if it is the case, the Martian ejector in the rigorous of Phobos contain a variety of ancient sedimentary soft rock materials with hopefully organics, like shown on the left, which is the lake bed mudstone at the Gale crater on Mars and the Curiosity landing sites. And you see that the whitish veins that would mostly comprised of the calcium sulfate in it. This calcium sulfate could reflect the condition of the ancient lakes of in ancient Mars. So these kind of materials, I really want to get this kind of materials to reconstruct ancient Martian sample conditions. So the conclusion is that the Phobos records provide a wealth of information on the ancient surface environment of Mars, not only with the Martian moons, but also the Martian materials as well. How can I get these samples? We have two sampling system. One is the coring system, figure on the this blue guys. That would access to the Phobos building blocks beneath to the surface greater than 2 centimeters, and the other sampling system, pneumatic sampling system. So that is the attached on the legs. That would give us a selective sampling of the Phobos very surface veneers, because the gases coming out are blowing and of the sufficient materials get into the horns and goes to the sample catcher. So the coring and numeric sampling system that maximize the MMX sample size, I believe. And then if you are a sample analysis scientist, that table would be very beneficial. We have a list of the lots of elemental combinations and then data types and the sample amount, but just want to give you some highlights. For example, that we have the ion microprobe and an infra ion microprobe that would give us a high precision oxygen and hydrogen and carbon and sulfur, nitrogen isotope that would give us an origin of the moon, as I shown. And also the we're gonna have mass spec and also give us a radiogenic isotope dating that would give us a formation age of the moon or capture the asteroid. And also the manganese chrome age that would give us an age. Argon age, that is a little bit offset. Argon age that would give us a distribution of impact. And also EPMA, TM, and Raman mass spectrometer give us a mineral chemistry and the crystallography that would give us regular physical properties of Phobos. And then here is the flow chart of the sample analysis. I think assuming the typical grain size of the 0.3 millimeters, we're gonna get about the 10,000 grains in 1 gram. So this 10,000 grains, we're gonna down to the 100 grains for the detailed petrography and mineralogy in situ isotopic analysis, and then further down, and we're gonna have selected. We are going to select the 10 to 20 grains for the bulk destructive analysis that would give us a high precision chromium, oxygen, titanium analysis. Another point is that we are going to use the 1 gram just 1/10 of the total mass for MMX. But the rest of that, hopefully greater than 9 gram for the international community, as for the Hayabusa mission and a Hayabusa 2 mission. So here's the last slide, the conclusions. The MMX spacecraft is scheduled to be launched in 2024 and return the greater than 10 gram of Phobos regress back to the Earth in 2029. The origin of Phobos and Deimos has been in DVH, capture of asteroid, or in situ formation by impact. So the MMX will provide a cruise to the origins and offer an opportunity to directly explore the building blocks and juvenile cross-mounted components and late accreted volatiles of Mars. And say MMX will continue or constrain the initial condition of the Mars Moon system and shed light on the source, timing, and delivery processes of water and hopefully organics into the inner rocky planet. Thank you.
Yes, thank you so much, Professor Usui. So let's see whether we have questions.
Yes, I'm gonna copy and paste some of the first questions, and for the rest of the audience, please feel free to text your question in the text box. So the first one is, I don't know if Professor Usui can see it. Can Phobos and Deimos be of different origins, have different origin?
Yes, if it is the capture of asteroid scenario, that might be possible. One is for D-type kind of asteroid, and the other is another type of asteroid. That is one of the case, but it's this is kind of a bit hard because, as I said, like dynamical properties of both the Phobos and Deimos are pretty much the same. Just the radius is different. So maybe still remote sense, still the scientist has struggled to make this kind of dynamical circular orbit into the two different origins. So yes, but very difficult. The answer is yes, but very difficult.
Okay. There was a second question. What is your bet on the origin of Phobos? So what do you think is the origin of Phobos?
My guess is the giant or kind of an impact origin is my guess, and to explain surface properties, I think these of the surface weathering or modification of the very thin surface veneer could reflect the D or T type spectra. Just an masking effect would erase the inside of the pristine materials. So my guess is that the Phobos Deimos could be the origin formed by a giant impact.
Okay. I don't know if you can read the questions. The next one is the sampling mechanism the same as that of the Hayabusa missions?
Totally no. Totally different. At Hayabusa and Hayabusa 2 is a it's weird. It's very weird for the turning on my screen cameras, but it's the Hayabusa and Hayabusa 2 is a touch and go. So not the landing missions. So sampler horn just touch the surface. So that is totally different. We have a coring system to get the large amount of the samples, and we want to have the stay on the surface of Phobos more than 2 hours and do some manipulation operations. So totally different sampling system. That is very challenging for us, new challenge. Thank you.
Okay, then we have another question regarding Can your mission provide information on the interior structure of Phobos?
Yes, but how deep? It depends on how deep it is. Just a couple of centimeters or greater than 5 centimeters, that would be accessible by the coring system. We also have information about the momentum of inertia. That is the one of the physical parameters represented by the interior structure. So, but it's not like we don't have a seismometer. Yes.
Okay. Another question from Professor Michel Blanc. First of all, he thanks you very much for the great talk. And he wonders if the grains you will retrieve from the satellite's regolith could have recorded neutrals or ions implanted from the primordial atmosphere of Mars, which was lost during its early history, giving access to some pieces of the atmospheric evolution scenario of Mars. I think it's a long question, so maybe if you can also read it in the chat box, maybe it's easier.
Yep, I can read it well. And then so the answer is yes. I really wanted to see atmospheric implantation on the Phobos regolith. So, but it's the energy could be very low. So we need a special analysis to detect the surface ions, like not like microns, but it's like less than a nanometer or something. But it's very challenging. So the sample coming back to the Earth in 9 years after that. So I think techniques should be improved by then.
Okay. Received another question. Why can't Phobos be of cometary origin?
Oh, the same. Same for asteroidal capture. If it is a cometary origin, so the it is we need to explain circular orbit. This is also very difficult to explain. So this is why we are not too much think of the cometary origin, but we will for sure know. We don't know yet, of course.
Okay. Couple of other questions. Professor Olivier Vitasse, could you leave a laser reflector on the surface of Phobos for future geodesy studies?
Unfortunately, no. But it's the now we preliminary design phase. If the after the preliminary design phase, we may see a bit of mass, a load. We may have a chance, but at this moment, we don't have a plan. But that is a very great point. Thank you.
Another question. You mentioned that Phobos regolith can contain an admixture of materials from different origins, impactor materials, Mars pristine material. Could there be a sampling effect that is depending on where from the surface of Phobos the material is collected, giving in each case very different indications?
It's we don't know yet. Is an answer at this moment. But my guess is that we have the Phobos and Deimos. At least the Phobos has a strong gardening processes. So as I said, although we have a blue and red units and Phobos, and mostly well mixed, could be homogeneous properties on the surface. So, but when we get the sample back to the Earth, we have grains by grains analysis that would give us some this kind of information. But it's the yeah, again, back to your question is that I do not think we have sampling bias on the as of regarding or in terms of the landing site, I guess, but we'll see. We'll see. We don't know yet. We will. The MMX is the first guy to review the high resolution remote sensing. So we will see the clear difference, heterogeneity on the Phobos surface. We'll see. Thank you.
Thank you. Another question here. Phobos is spinning towards Mars because of tidal effect. Could there be satellites lost by surface impact B5?
Could there be a satellite lost by surface impact? Yes, I think so. So this question means that the so ancient satellite that has been already lost. So the Phobos is this a question that like more of the surface? Okay. Yeah. To answer this question, yes. I think that we might have ancient extinct satellites, I guess, if the giant hypothesis is correct, because the some giant impact hypothesis proposed that there is a thick debris disk to form many Martian moons. So not two, but more than two. So other than two could have been lost to impact.
Okay. Professor Veronica Remondini, I want to thank you for this webinar, and I'm just an Italian space enthusiast and do not understand 100%, but she's very enthusiastic about the webinar. She will follow you. Also, the webinar will be, the recording will be published online, and therefore everyone will be will have the chance actually to rewatch the webinar once on our YouTube video, on our YouTube channel or on our Bilibili Chinese channel. So no question here, but just a thank you for your great presentation.
Thank you. I enjoyed it too.
Any other question eventually? I see nothing coming in, but for the participants, this is your last chance. If not, if there is no other question, I think we can, yes, we can end the webinar. Professor Ip?
Yes, thank you so much for this very, very interesting talk. I mean, sorry for the interruption, a little bit interruption, but I hope that we will not repeat that. And we look forward to the successful return of the Phobos sample. And we will book you onto a future talk in this series. And thank you so much.
Thank you very much. Thank you everyone for joining.
Thank you. I really enjoy it. And sorry for, I guess my network is not so great. Probably not, but it's anyway.
No problem. Thank you very much. Bye. Bye-bye.
Bye.
Bye. See you
Bye,
sometime in the future after the COVID-19 situation is getting better.
Very
So.
important. Happy New Year in advance. Bye-bye.
Bye.